The space between the stars is not empty, not even close. Right now, spread across the galaxy in clouds so vast they dwarf entire solar systems, there is an ocean of gas, dust, and molecules. And some of those molecules are the same building blocks that eventually made you. That is not a metaphor. That is chemistry happening in the dark, billions of miles from the nearest sun. What we're diving into today is called the interstellar medium, the ISM, and it is one of the most overlooked, most extraordinary environments in the known universe. Most people picture space as a perfect vacuum, a cold, featureless void. But that picture is wrong in almost every interesting way. The interstellar medium is dynamic, it is chemically active, and it plays a direct role in building new stars, new planets, and potentially new life. Stay with me, because the deeper we go into this invisible ocean, the stranger it gets. Let's start with what the interstellar medium actually is. If you could scoop up a cubic centimeter of the ISM, about the size of a sugar cube, you would find, on average, roughly one atom. Just one. Compare that to the air around you right now, which contains about 27 quintillion atoms in that same space. By any human standard, the interstellar medium is extraordinarily thin. And yet, multiply that near emptiness across the staggering volume of our galaxy, and you end up with something substantial. The ISM accounts for roughly 10 to 15% of all the visible mass in the Milky Way. That is hundreds of millions of times the mass of our Sun, just floating between the stars. It is not all the same stuff either. The interstellar medium has layers, regions, phases, almost like different weather systems in an atmosphere. There are hot, tenuous bubbles of gas heated to millions of degrees by supernova explosions. There are warm regions of ionized hydrogen glowing in ghostly pinks and reds. Those are what we photograph as nebulae, and they are genuinely beautiful. And then there are cold, dense molecular clouds, where temperatures drop to just 10 degrees above absolute zero. Those frigid clouds are where stars are born. And they are also, it turns out, where chemistry gets interesting. Here is the open question I want you to hold on to. How does chemistry even happen in the coldest, darkest, most isolated regions of the galaxy? There are no lab benches out there, no liquid water, no energy input from a nearby star. And yet astronomers have detected over 240 distinct molecular species in the interstellar medium. 240. That includes water, ammonia, formaldehyde, ethanol, yes, alcohol, and molecules far more complex than anyone expected to find floating in deep space. We will come back to how that's possible, because the answer genuinely surprised the scientists who figured it out. First, let's talk about dust.
When astronomers say interstellar dust, they do not mean household dust, clumps of dead skin cells. Interstellar dust grains are microscopic particles, typically less than a micrometer across, made of silicates, carbon compounds, and ices. They are so small that individual grains float freely through space for millions of years. And they do something crucial. They block and scatter light. When you look at a dark patch in the Milky Way, a region that looks conspicuously empty, you are almost certainly looking at a dense dust cloud blocking the stars behind it. The most famous example is the Horsehead Nebula. That dramatic dark shape is not a hole in the universe, it is a wall of dust. But here is where dust stops being just an obstacle and starts being a protagonist. The surface of a dust grain is one of the most productive chemistry labs in the galaxy. In the freezing cold of a molecular cloud, atoms and simple molecules drift through space until they collide with a dust grain and stick to its surface. There, they are held just long enough to meet another atom, react, and form something more complex. Hydrogen atoms combine on grain surfaces to form molecular hydrogen, H2, the most abundant molecule in the universe. Water forms this way too. And over time, these grains accumulate icy mantles of increasingly complex chemistry, all driven not by heat, but by cosmic rays and ultraviolet radiation penetrating from distant sources. Think about what that means. The most complex organic chemistry in the universe is not happening in a warm, sunlit ocean. It is happening on the frozen surface of a dust particle in a cloud of gas so cold that human technology has barely matched it in a laboratory. Now here is the payoff to that open question. How does complex chemistry form in places that seem to have nothing going for it? The answer is time. Vast, incomprehensible amounts of time. A molecular cloud can persist for tens of millions of years. In that time, even incredibly rare collisions between atoms become statistically inevitable. The interstellar medium does not need to be efficient, it just needs to be patient. And the universe is extraordinarily patient. This brings us to the most staggering part of all this, the part that should genuinely shift how you see yourself in relation to the cosmos. Those molecular clouds, packed with their slowly accumulating chemistry, are the raw material for everything. When a molecular cloud collapses under its own gravity, it forms a new star. The material that doesn't fall into the star, the dust, the ice, the organic molecules, forms a disk around it. That disk becomes planets. And the molecules that were assembled over millions of years on the surface of a cold dust grain end up on the surface of a rocky world. Scientists have found amino acids, the building blocks of proteins, inside meteorites that formed from the same kind of material as the early solar system.
We have detected glycine, the simplest amino acid, in the gas surrounding a star-forming region. The chemistry that began in the interstellar medium did not stop when our solar system formed. It arrived here. It became part of the oceans. It became part of life. You are not just made of stardust in the poetic sense. The specific molecular precursors to biology were assembled in the freezing dark between the stars, delivered to this planet, and incorporated into the very chemistry that makes you alive. The interstellar medium is not a backdrop. It is an origin story, and we are only beginning to read it. Missions like the James Webb Space Telescope are now detecting the chemical fingerprints of molecular clouds with unprecedented precision, mapping the distribution of water ice, carbon compounds, and complex organics across star-forming regions. Every new detection redraws the map of where life's ingredients can be found, and that map keeps getting larger. So the next time you look up at a clear night sky and see the dark gaps between the stars, know that those gaps are not empty. They are teeming. They are ancient chemistry in motion. They are the universe quietly building its next act. If this changed how you see the space between stars, hit subscribe. We go this deep every single week. And next time, we are asking a question that keeps astronomers up at night. Could there be planets orbiting not around stars, but drifting freely through the interstellar medium itself? And could anything live on them?